Imagine if every time a sinkhole opened on Earth, a new mountain just sprung up right beside it. The result would be unlike any mountain you've ever seen before. This is the kind of bizarre natural process that has been playing out on Io for billions of years, as its surface rises and falls under the relentless pull of Jupiter's gravity. And this world is real. Out here, deep into space and far away from the sun, you might expect everything to be frozen and lifeless. And yet, we find images like this, captured by one of NASA's most advanced research probes that shows us these bizarre structures seemingly created by a process that is unlike anything we know on Earth. Jupiter's moon, Io, is more alive than any other body in our solar system. Its rocky surface is caught up in a raging battle between fire and ice. Meanwhile, scientists on Earth have only just begun to uncover the hidden forces that are driving this chaos. The Jupiter system is home to nearly 100 officially recognized moons, a number that continues to grow as we discover new objects orbiting the giant planet. Most of them are very small, but 4 are exceptionally large. We call these the Galilean moons, as they were first recognized by the 16th century astronomer Galileo Galilei, using one of the first telescopes ever made. The outer 2 moons are the largest, Callisto and Ganymede. Both are solid orbs of ice and rock with dead, heavily cratered surfaces. Second in line is Europa, which is made from a thin, smooth sheet of ice floating on a vast ocean of liquid water. It's one of the most promising locations in the solar system to find extraterrestrial life. And then closest to Jupiter is Io, sitting about 350,000 kilometers above the cloud tops of the gas giant. That is not much farther than the distance between Earth and our moon, and it is roughly similar in size, just slightly larger and more massive. Io is actually the densest moon in our solar system, mainly because it is composed almost entirely of rock and metal. While most of the other large moons in this region are made of ice mixed with rock. The contrast is so dramatic that Io is thought to contain the least amount of water of any known object in the solar system, even drier than Mercury, the closest planet to the Sun. But what truly sets Io apart is what is happening across its surface. This is the only place beyond Earth where we have confirmed that volcanoes erupt on a regular basis. In fact, Io is the most volcanically active world in the entire solar system, with as many as 400 active volcanoes scattered across its surface. This was first discovered by the Voyager 1 probe during its flyby of Jupiter in 1979. Even from a distance of 20,000 kilometers, using relatively primitive and low-resolution cameras, Voyager managed to detect 9 separate volcanic eruptions blasting material high above the moon's surface. These intense lava flows stand in sharp contrast to a world otherwise locked in deep cold. Outside of these volcanic regions, the surface temperature on Io can fall to around minus 130 degrees Celsius. We know that the Sun is far too distant to provide any meaningful heat to the Jupiter system, so the question becomes, where is all this energy coming from? To understand this, we need to recognize that Io occupies a very dangerous position. At such a close distance to Jupiter, it is just far enough away to avoid being pulled in or torn apart by the planet's immense gravity. But that does not make it safe. Jupiter's powerful gravity still pulls strongly on Io's surface, stretching the rock and warping its shape. And at the same time, there are 3 other large Galilean moons nearby, and they apply their own gravitational influence. While much weaker than Jupiter, it is still enough to pull Io in the opposite direction and disturb its orbit. As a result, instead of following a perfect circle, Io moves along an elongated oval path. This means that at times it is very close to Jupiter, and at other times it drifts farther away. Because of this, It never experiences a consistent gravitational pull, instead cycling back and forth roughly once every 2 days, continuously being stretched, released, and reshaped as it travels. The outcome is that Io undergoes extremely powerful tidal bulging. This is the same effect that we observe in Earth's oceans. Our own moon exerts enough gravitational pull to lift the water, creating high and low tides. On Earth, the average rise of the ocean is only about half a meter. Coastal regions can experience different tidal ranges depending on geography. But out in the open ocean, the variation is relatively small. On Io, however, Jupiter's gravity does something far more extreme, raising the surface by as much as 100 meters when the two bodies are at their closest point. And this is not just moving water, it is stretching solid rock and giving the entire moon a slightly elongated, egg-like shape. All of this constant stretching and compression acts like a powerful engine, pushing energy deep into Io's interior and fueling its intense volcanic activity. But these volcanoes do not behave the same way as those on Earth. When you think of a volcanic eruption, you likely picture a tall, cone-shaped mountain with lava and ash bursting from the top. On Earth, these form where tectonic plates collide and force material upward from below. Io, however, has no plate tectonics, so lava tends to erupt through fractures created by continuous gravitational stress. The initial burst of energy can launch lava dozens of kilometers above the surface, and beyond that, plumes of sulfur gas can rise for hundreds of kilometers into space. Sulfur is also a common element in volcanic activity on Earth. If you have ever seen a piece of lava rock covered in small round holes, those are formed by pockets of trapped sulfur gas. On Io, this leads to the formation of a thin sulfur-rich atmosphere surrounding the moon. Depending on how active the volcanoes are at any given moment, this atmosphere can range from about 1/3 the density of Earth's to nearly twice as dense. Much of the sulfur that is released eventually falls back down, coating the surface. This process is what produces the striking range of colors visible from orbit, with yellow regions formed by sulfur crystals created in the extreme cold, essentially forming a kind of frozen sulfur snow. The white and blue regions are made of frozen sulfur dioxide found in the coldest shadowed areas. The green tones come from sulfur monoxide, created through interactions with Jupiter's radiation belts in the upper atmosphere. And the red areas mark regions of recent volcanic activity where sulfur is still being heated. As mentioned earlier, volcanic activity on Io does not build mountains or shield structures like on Earth. Instead, after the initial eruption, the surface often collapses inward, and molten rock fills these depressions, forming vast lava lakes. The largest of these is called Loki Ara, stretching about 200 kilometers across. At its center lies a large island of solidified rock, surrounded by a constantly churning lake of molten material. Given all this volcanic activity, you might assume that Io is structured like Earth, with a solid crust floating above a global magma ocean. However, evidence suggests otherwise. Spacecraft studying the Jupiter system have measured Io's gravity field and found it to be highly uneven. This indicates that magma is not spread evenly beneath the surface, but instead exists in localized reservoirs of molten rock, concentrated in regions where tidal forces are strongest. What this means is that there are hundreds of independent volcanic engines hidden beneath the surface, so each volcano behaves in its own slightly different way. Now here comes another mystery. If volcanoes and plate tectonics are not responsible for building mountains on Io, then where did these structures come from? This formation is known as Steeple Mountain, rising somewhere between 5 and 7 kilometers high. It is one of the most recognizable features on Io, mainly because it resembles the sharp spire of a church tower, or even the Eye of Sauron. We are able to observe such remarkable detail thanks to data gathered by NASA's Juno spacecraft, which reached Jupiter in 2016 on a 5-year mission to study the planet's atmosphere. After completing that objective, Juno was reassigned to explore the 4 Galilean moons. The spacecraft carried out 2 close flybys of Io, the first in December 2023 and the second in February 2024, passing within about 1,500 kilometers of the surface. What Juno revealed may be the most unusual landscape anywhere in the solar system. Scientists soon realized that Steeple Mountain is just one of many tall, needle-like peaks scattered across Io. The tallest of these rises to about 18 kilometers, nearly twice the height of Mount Everest. What makes this even more fascinating is that, unlike Everest, these formations do not exist in clusters or mountain ranges. Instead, they appear as isolated structures, standing alone like solitary spikes rising straight into the sky. This suggests that they did not develop gradually over long periods of time. Rather, they seem to have erupted suddenly from the ground in dramatic fashion. Researchers believe this process is still connected to volcanic activity, but in a much more unusual form. Earlier, we discussed how lava flows can cause sections of Io's surface to collapse, forming massive lava lakes. The idea is that this downward pressure forces nearby rock upward. Imagine if every time a sinkhole formed on Earth, a new mountain suddenly rose right beside it. That is essentially what we are seeing here. The result is a type of mountain unlike anything found on Earth. This strange geological process has likely been unfolding on Io for billions of years, with its surface constantly rising and falling under the relentless influence of Jupiter's gravity. Unfortunately, these stunning views may be among the last we capture. As Juno gradually runs out of fuel, it will eventually be replaced by 2 new robotic missions exploring the Jupiter system. One of them is JUICE, short for Jupiter Icy Moons Explorer, developed by the European Space Agency and launched in 2023. When it reaches Jupiter in 2031, JUICE will focus on 3 of the Galilean moons, Ganymede, Callisto, and Europa, studying their icy surfaces and hidden oceans beneath. Then there is NASA's Europa Clipper, launched in 2024 and expected to arrive in 2030. As the name suggests, this mission is dedicated to exploring Europa, with the main goal of searching for signs of life within the ocean hidden beneath its icy crust. That leaves Io somewhat overlooked, with no missions currently planned to visit it in the near future. This is not because Io lacks scientific value, but rather because its true complexity has only recently been revealed through Juno's observations. And of course, it is not considered a likely place to find life, which lowers its priority. However, NASA's priorities are evolving. New leadership is bringing fresh direction, and groundbreaking rocket technologies are beginning to reshape what is possible in deep space exploration. And sometime in the not-so-distant future, we may be exploring the deeper reaches of the solar system with the same level of detail that we now apply to Mars and the Moon. Until that moment arrives, one thing will remain with us: Steeple Mountain.